Hello everyone, today let's take a look at Quantipus number 80, another combinatorics question, and this is going to be the first set partitions question. So how many ways can 8 identical, keyword identical balls be partitioned into 4 indistinguishable boxes? Okay, first things first, this is not a stars and bars question, even though it's phrased very similarly. In stars and bars, we had distinct boxes, right? And in this one, we have identical boxes. Right, this was the stars and bars setup. If this said distinct boxes, then we would solve it like this, right? Where we're summing up the number of ways that we can add to 8. For instance, we could have 4 here, 3 here, 1 here, and 0 here. In this case right here would be treated differently if we swapped these two, right? If x2 had 4 and x1 had 3. And that's because we have distinct labels here, right? We're labeling x1, x2, x3, x4, but in this situation, we're saying the boxes are indistinguishable. So in our situation, we're removing these labels. We're saying 3, 4, 1, 0. Well, that's just going to be exactly the same as 4, 3, 1, 0 or 4, 3, 0, 1. Any permutation of these is going to be the same. So if we were counting them as distinct boxes using stars and bars, well, we know how to do this. We have 8 objects and we need 3 bars to split into 4 groups. So 11 choose 3, which is equal to 165. So now to solve this problem, you might say, okay, well, we can figure out the number of ways for unique boxes, so let's just kind of divide out the uniqueness by dividing by 4 factorial. And the logic behind this thinking is that, okay, for each one of these partitions, I can permute them individually in 4 factorial ways, right? So we're going to be overcounting in here by a factor of 4 factorial. But you can tell that this isn't going to work just by looking at it, because you see the 4 factorial down here is 24, and you know that 24 cannot divide 165. So this method is wrong. So why is this actually wrong? Well, it turns out that not every partition overcounts in here by this same factor. This one did because all the numbers were unique, but if, for instance, I had 4, 2, 2, and 0, well, how many distinct ways are there to give these 4 numbers to my 4 variables? Well, this is just a multinomial problem, which is going to be 4 factorial on 2 factorial because we have this repetition here. And this is not equal to 4 factorial. So this is all just to show that we cannot divide by one uniform factor to get rid of the uniqueness here and make them indistinguishable. And the crazy thing about these integer partition things is there's actually no easy way to think about it like this. There's no unique formula that we can use. So when I'm distributing identical objects to identical boxes, there is no formula. There is nothing that we can use to solve this easily, right? So to solve this, we're just going to go back to the caveman days and then just list out every single possible partition and then just count them up. So let's just go down and actually do that now. And when we're counting these out, it's going to be helpful to group them into different categories based on the number of boxes that are empty, and the reason why will come up later. So let's first start off where we have 3 boxes empty, right? So everything is in one box. So now how many ways can we do this? Well, we can have 8 in one box, 0, 0, 0. And that's clearly the only way to partition it when we have 3 boxes empty. So now let's move on to 2 boxes empty. So if we have 2 boxes empty over here, we could either have 7, 1, or we could have 6, 2, 0, 0, or we could have 5, 3, 0, 0, or we could have 4, 4, 0, 0. So now let's move on to our 1 box empty case. Okay, so we're leaving 1 box empty, which means we need at least 1 in all the others. So we must start with 6, and then we could have 6, 1, 1, 0. So that's the only way with 6. Let's move on to 5. I could have 5, 2, 1, 0. And that's the only way with 5. So let's move on to 4. I could have 4, 2, 2, 0. Or with 4, I could also have 4, 3, 1, 0. Then I could have 3, 3, 2, 0. So that's going to be my total with 1 box empty. And now let's move on to our final case where we have 0 boxes empty over here. So every box needs to have at least 1. Let's start off where we have 5, 1, 1, 1. Or I could have 4, 2, 1, 1. And my final partitions are just going to be 3, 3, 1, 1. Let's go 3, 2, 2, 1. And then we can go 2, 2, 2, 2. And it turns out that these are the only partitions that I can make. So now let's count them up. We have 5 over here. We have 1 over here. We have 4 here. And we have 5 over here. So that's going to give us a total of 15, which is going to be our final answer. So this is how we have to solve these integer partition questions, but notice how it makes the restricted cases a lot easier. For instance, if they ask about the number of ways where the number of elements in each box is unique, okay, I'm just going to count them out anyways. So now I can just count them out. I have this one here. We can say this one. We can say, okay, not these. We could say maybe, yeah, actually that's it. If they say find the number of ways to do this such that 0 boxes are empty, okay, I know what it is because I just listed them out. So there's going to be 5. What about the cases where the number of elements in each box is odd? Okay, right here, boom and boom. Okay, so now conclusion. When I'm doing identical balls into identical boxes, I'm going to need to list them all out. And we got 15 in this case.